this video, we're going to review how to balance equations. We'll do a few examples together, and then you should go practice as many as you can so that this can become second nature to you, because it'll be very important for this unit and the next unit in chemistry, and basically all the chemistry courses that you take in the future. So a balanced equation is one that follows something called the law of conservation of mass, which basically states that you can't really destroy and create matter, which means that if you have, let's say, 5 grams of reactants, well, you need to have 5 grams of products in the end. So if you're, let's say, baking a cake and you have 3 pounds of ingredients, well, your cake should weigh 3 pounds when it's done. It shouldn't weigh more than that. So if you have 3 pounds of ingredients and all of a sudden you have a 20-pound cake, well, something weird happened and it was magic. It wasn't science. So you have to make sure that when you're doing a reaction, you represent that reaction using the law of conservation of mass. And the way to do that is to have a balanced equation. So how do they relate? Well, a law of conservation of mass states that the mass of the reactants is equal to the mass of the product. So if you have 5 grams of reactants, you end up with 5 grams of products. And the way to make sure that your reaction follows that is by balancing the reaction, balancing the equation, which basically means that you can account for all atoms that were used on the product side. So if you have a balanced equation, for example, if I start off with 2 H's here, 2 hydrogens, I should have 2 hydrogens on the product side in the end. If I start off with 2 oxygens, I should have 2 oxygens on the product side in the end, which I don't here. So this is not balanced, and this does not follow the law of conservation of mass. It's kind of like if you're asking for change. If you have a $10 bill and you want loonies in return, in exchange, you should get 10 loonies. It has to be equivalent. It has to conserve the amount of money that's there. So a skeleton equation does not follow the law of conservation of mass, but a balanced equation does. So here you can see many steps to balancing equations. You should read through them and then attempt these examples. I'll walk you through these 3 examples here, and then you can try the next examples on the following page, and then find other practice problems online. There's plenty of resources out there and plenty of videos you can use to become a pro at this. I also recommend that before watching this video or attempting balancing, you should watch the video that goes over how to count atoms in different types of compounds, and that way you'll be much better off when it comes to balancing equations. So there is a grade 10 review video for that. Please make sure you watch that before doing this so you're familiar with that. You'll notice there's an order given with which you should try to balance components in a reaction. So usually you want to start off by balancing your metals, followed by your polyatomic ions, followed by your nonmetals, then oxygen, and then you leave hydrogen for last. And you can remember that using the mnemonic MINO, M-I-N-O-H. So one more thing I want to mention before we actually begin is you'll notice you have small numbers here. Those are your subscripts. You can never change the subscripts to balance an equation. Otherwise, you're changing the chemical, you're changing the compound. Never modify those subscripts. The only thing that you can change is the number in the front called the coefficient. So there's a big number written in the front called the coefficient. That's the only thing you can modify to balance your equation. So when you start off, what you want to do is you want to start off by counting. Just start counting to see if you have the same number of elements on of each type on both sides. So for H, on the left side, we have 2 right now. And on the right side, we have 2 as well. For O, on the left side, we have 2. And on the right side, we have 1. So right away, we can tell that this is not a balanced equation. Sometimes an equation is balanced as is, but right now this is not balanced. Our O's are not balanced. We don't have enough O's on the product side. So this is not following the law of conservation of mass. So to balance it, you cannot change a subscript. There's a subscript of 1 there, it has to remain as that. What we can do is we can put a big 2 in the front, coefficient of 2. When you do that, that coefficient multiplies everything in the compound. So now we have 4 H's and 2 O's. So 2 times 2, 4 H's, 2 times 1, 2 O's. So our O's are balanced, but now our H's are not. So this is really a balancing act. It's going back and forth until everything is balanced. So let's go to the left side. We don't have enough hydrogens now to fix that. So I have 2 hydrogens. To get 4, you simply put a 2 in the front of the hydrogen. And now we have 4 hydrogens. So now we have 4 hydrogens on the left side, 4 hydrogens on the right side. That's balanced. 2 oxygens, and 2 oxygens on the right side. So now we have a balanced equation. We have the same number of atoms on both sides. There's a total of 6 atoms on this side, and each type of atom is balanced on both sides, and a total of 6 atoms on this side. Notice how there's no coefficient required for the O2. In reality, there actually is one. It's 1. It's an implied 1. Okay? If there was no oxygen, we just wouldn't write it down. So when you write an element down or a formula down without a coefficient, it means 1. On the quiz or a test, they're going to ask you to put the 1 on the line just so that you're showing all your work. But in reality, when you're writing an equation out, you don't have to put 1 if there's only 1 there. So let's go and try the second problem below. You should try it yourself first, and then so pause the video and then come back to check with me after you've tried it yourself. So here we have zinc, some chloric acid, and they're reacting to produce some H2 gas, and then some zinc chlorate. So you'll notice that we have polyatomic ions in this case. You can actually balance these polyatomic ions as a single unit. You don't have to count individual CLs, individual O's. When the polyatomic ion appears on both sides, you can treat it as a single unit. Okay. So we're going to start off with our metals. So zinc, on the left side we have 1. On the right side we have 1. So zinc looks fine. Let's go with our ions, the ClO3 minus. So you need to recognize your polyatomic ions here. We have 1 on the left side, on the reactant side, and notice 2 because it's in brackets, and then there's this 2 subscript outside there, 2 on the product side, the right side. And let's take a look at our H's. Here we have on the reactant side, we have 1, and on the product side we have 2. So our zinc looks fine, so our metals are balanced, but our chlorates and hydrogens are not balanced, 1, 2, 1, 2. So let's start off by trying to balance our polyatomic ions. We have 1 chlorate on this side, 2 chlorates on this side. So to balance it, let's put a coefficient of 2 over here, and let's right away go into our table and change whatever had to change. So now that we put a 2 here, we have 2 hydrogens. Oh, look at that. We balanced our hydrogens while trying to balance our chlorates. We now have 2 chlorates. Now everything is balanced. 2 chlorates, 2 chlorates, 2 hydrogens, 2 hydrogens, 1 zinc, 1 zinc. Just go ahead and fill in the rest with 1s to show that you know what you're doing. And always go back and double check your count, of course. So zinc 1, zinc 1. Hydrogen, 2 times 1 is 2, 2 over here with the subscript. Chlorates, 2 times chlorate as a whole is 2 chlorates. And then over here, we still have 2 chlorates. Now you could also have done it by counting the individual atoms. It would work just fine. You'll notice 2 times 1 chlorine is 2 chlorines, and then 2 times 1 in there, that's 2 chlorines. 2 times 3 oxygens is 6 oxygens. 2 times 3 in here is also 6. So you could have done it with individual atoms, but it's just a lot easier to group them together when the polyatomic ion, the same one, appears on both sides of the equation. If it doesn't appear on both sides of the equation, if it's, let's say it's only on the reactant side and it breaks up into something else on the product side, you have to treat them as individual atoms. Otherwise, you'll get the balancing wrong. So now we'll try the last one below. That one's a bit trickier. I'm going to teach you a little bit of a maneuver around it to get the right answer. So here we have a combustion reaction, and we usually like to start off with our non-metals and then go to oxygen and then go to hydrogen. So let's try that out. So we have carbon. We have 2 on the left side, and we have 1 on the right side. So I'm going to try to balance it. I'm going to put, well, I'll do that afterwards. Let's just count first. Counting is always the safest way to go. For oxygens, we have 2 on the left side. And then on the right side, we have 2 here, but don't forget to count the other one over here. That's 3 total. And let's now count our hydrogens. So we have 6 on the left side and 2 on the right side. Now it looks like our video time is running out. So I'll finish this example in another video just quickly. So this will be part 1 of balancing, and I'll post another video called part 2 in just a bit.